Okay, so let's continue and let's talk about what evidence do we have that this Big Bang ever happened. Well, actually, we do have quite a bit of evidence, and we'll talk about those in turn. All right, so what's our primary evidence? Well, we've detected the leftover radiation from the Big Bang. That's a big one. And the Big Bang Theory correctly predicts the abundance of helium and other light elements, which is important. And of course, the expansion of the universe was our first clue. Okay, so how do we observe the radiation left over from the Big Bang? Seems kind of crazy. How do you do that? Well, in fact, you can, and the first observation of this was made by Penzias and Wilson in 1965, and we're going to see a video about that. Hold on one second.
380,000 years after the Big Bang, the universe had expanded to the size of the Milky Way. It had cooled from billions of degrees Fahrenheit to a few thousand. As it cooled, the electrons slowed down. The universe was now ready to make its first true elements. One of the scientists who discovered this critical moment in the story of the universe was Arno Penzias. 1963, 30-year-old Penzias and his 27-year-old colleague Robert Wilson began work on a new antenna in New Jersey. Initially, they were only studying cosmic radio waves, but they would stumble on one of the greatest discoveries of all time. As they started to test their equipment, they detected an unexpected background noise.
It was additional signal, and it appeared to be coming from the sky. We eliminated very carefully the ground, even the solar system, because we did this winter to summer, seasonal variation, man-made sources of equipment. All these things were eliminated.
In desperation, the two scientists began to wonder whether the strange signal might have another, more earthly origin. They found there were pigeons roosting in the antenna, and it was covered with droppings. They wondered if the pigeons were the source of the strange signal. There was only one solution. The droppings and the pigeons would have to go.
We finally got around to removing the pigeon droppings. We also had to remove the pigeons. That was a difficult problem because they turned out to want to come back, and we mailed them off to another site.
But even with the troublesome pigeons gone, the mysterious signal would not disappear.
And so we were left with the almost inescapable conclusion that this radiation was coming from the sky. I could not account for it.
The strange signal detected by Penzias and Wilson would turn out to be one of the most important scientific discoveries of all time. But the explanation for their mystery background noise starts not with sound, but with the birth of light. We usually take light for granted, but in the early universe, 13 billion years ago, we would see nothing at all. Light was trapped. The universe was foggy. Imagine a flashlight beam in a fog of smoke. The light bounces back and forth between the smoke particles and is trapped. In the hot baby universe, a dense fog of electrons blocked the light from escaping. But as the universe continued to expand and cool, the electrons slowed down. Protons then grabbed these calmer electrons to form complete atoms of first hydrogen and then helium. The universe was suddenly much less crowded with electrons. The fog lifted, and light was no longer trapped. It hurtled out across the universe, creating a blinding burst of light.
Had we been there, we would have suddenly seen this opaque universe become transparent. Suddenly the fog would lift, and we would see a flash of light coming from everywhere around us. It must have been a spectacular moment.
Over time, this burst of light dimmed and cooled and became microwave radiation. It was this faint 13 billion year old microwave signal that Penzias and Wilson picked up on their antenna. What they heard was the quiet echo of the moment the universe formed the first atoms.
It's really the light from the origin of the universe. If you have an old FM receiver, if you tune between channels, turn the knob, and it doesn't capture it and pop to a station, go to a part where there's none, you hear a, that's what we call noise. If you have a good radio set, 1/2 of 1% of that is actually the sound of the Big Bang.
And we can also see the moment when the first elements were created. If our television is not tuned to a station, a tiny fraction of the noise is radiation from 13 billion years ago. But this radiation is not the only reminder of the birth of the universe. Even the water we drink is a memento.
And it's kind of amazing to think that every time we take a drink of a glass of water, we're drinking in atoms that have been around since the Big Bang, the hydrogen atom.
Over the next millions of years, the young universe continued to expand, cool, and get dark again. So far, the universe had only made hydrogen and helium atoms. But the world we live in is made from more than 100 different kinds of elements.
So you know the rest of that story, right? That the first stars formed, mostly hydrogen, and began fusing to helium, and then fusing to heavier elements, and the rest is history, right? But this discovery was really the discovery of that time that light became free in the universe. Now, light wasn't in the microwave range at that time, but as time went on and the universe was expanding, right, it's like the light waves got stretched, and they became microwaves, which are very close to sort of radio waves, right, in their wavelength. Okay, so again, background radiation from the Big Bang has been freely streaming across the universe since the atoms formed at that time, at 380,000 years ago. Okay, so what we detected was really the black body radiation from that. So you can think of it as, you know, detecting the sort of flash of light that was described. I like to think of it more as detecting the black body radiation from that particular time. And you can see that the observed spectrum of this cosmic microwave background matches the theoretical model extremely well. So we really have great evidence for the Big Bang. And we have a satellite called WMAP that gives detailed pictures of the structure of this microwave background. So again, if you think about this as sort of light that's been sort of stretched into the microwave range, you can see here that you know, this representation that you see is kind of, think of this as the all sky, right? And what they're representing here is the slight differences in temperature from all the different places in the sky. And if we didn't have those slight differences in temperature, then nothing would have ever formed in the universe, because this is sort of a footprint of density changes or density differences in the early universe. And if you didn't have any density differences, then nothing would sort of coalesce, right? So if you didn't have a region somewhere where it was slightly more dense, then that region would never coalesce into anything like a star. So all those sort of fluctuations you see in this picture are really a footprint of density changes. Okay. Now, what about the abundances of elements? How does that support the Big Bang? Well, remember that protons and neutrons combined to make long-lasting helium nuclei when the universe was about 3 minutes old, right? And Big Bang Theory really has a prediction of that you should have about 75% hydrogen and 25% helium by mass. And this prediction matches observations of the primordial gases. So it's very clear that the abundance of the elements points towards the Big Bang. Now, it also points to us having about 4.4% normal matter, right? Which is just like what we saw for dark matter. So this is more evidence for WIMPs, right? That our prediction really predicts that we should only have about 4.4% normal matter. So this is a lot of really good evidence for the Big Bang actually having occurred. Let's try a question. So pause the video and answer the question.